My name is Nicholas. I'm a student here, and our first speaker today is Professor Levenson-Falk from the Levenson-Falk lab at USC. Professor Falk just recently got promoted, if I'm not mistaken, to associate professor, so maybe we should congratulate him on that too. So Professor Falk works on superconducting qubits, and he's going to talk to you guys about a little bit of an overview of what you can expect this whole week. So from the beginner as well as the advanced track, the different talks, the workshops, the Thursday the Thursday panel and all the other networking events. We also have a Discord channel. He will show you guys a QR code, how you can join that, and there we can discuss anything about the device workshop or generally, on devices. And with that, without further ado, let's get started.
Thanks, Nicholas. So I just need to start by acknowledging Nicholas and Cody and Alexander and all the members of the Student Association here who've just done incredible work to get this going together. This was something that I told them we shouldn't do until the fall or next spring because we needed that much time to get it together, and I was completely wrong. So good job, guys. Also need to thank our sponsors who really have made this all possible, many of whom will have some people speaking, so you'll get to hear from them. So I want to just start off by making sure everyone's on the same page, and this is one of the few things that's going to have the advanced people and the beginner people all listening to the same thing. I'll try not to go too fast, and I'll try not to bore everybody, but I just need us to have the same terminology, the same nomenclature, so we all know what each other are talking about. Let me just start by going over what we're going to try to do here. Hey, guys, can you just say that? Right. For those of you who are beginners, for those of you who are new, have not made devices before, we're going to try to teach you how to do that. As far as I know, this is the first formal education of that has ever been done, which needs to change. So we are going to also try to see what works and what doesn't. You all get to be our guinea pigs, and we're going to try to spin some of these things out into bigger projects. There really does need to be a textbook for this stuff. If you want to help contribute to writing a textbook, you don't need to do anything. Just wait. Dan Sank will come find you. If you don't want to do that, then just avoid it. For those of you who are experts, there's new techniques coming out all the time. People are doing really exciting work on this stuff, but a lot of it isn't getting spread around. I think journals have been sort of unfortunately hesitant to publish purely design-related work. So a lot of it doesn't get disseminated as much as it should. Let's try to fix that. Also, there are some problems that we desperately need to solve. Let's try to agree on what they are and maybe even agree on how to solve them. And probably that solution is going to involve a lot of people spending a lot of time and effort, which also requires money. So we're going to try to tell the grant agencies exactly what we come up with. All right, so experimentalists, who has experienced this? Your theorist comes to you and theorist comes to you and says, I have the algorithm. It's got exponential speed up. It only needs 10,000 qubits. Like you can get away with 6 nines fidelity. That's all I need. Just make me this. Like, cool. And look, I did the work for you. It's not like an algorithm. It's a gate sequence. All right. Yeah, I appreciate it. Then, why is that? Okay, that's just, you can still see it here. This really great theorist comes to you and says, you know what? Screw that guy. I know what you need. Make me this effective Hamiltonian. And for those of you who are sort of younger in this field, it was like a revelation when people like Yen started even doing this. Like, this was just incredibly new. It was hard for us to get theorists to even like think of the idea of a qubit as a physical object. So someone who was doing this already gets a gold star. But unless they're giving you a very, very specific thing that you already know how to make, this is nothing. Now, if you're really lucky, they come to you and say, give me this circuit diagram. And, you know, as someone who does this is basically your angel. They have figured out all of the difficult circuit QED theory to say, this is going to be a qubit. This is going to be a good qubit system. What you need to do is faithfully implement this. And that is hard enough. Because what we're trying to solve here is the inverse design problem. You have some target, typically, you know, if you're lucky, you get the gold star theorist and you've got some effective Hamiltonian space that you're targeting. But you don't work in effective Hamiltonian space, you work in design space, you make physical layouts. And the question is, how do you do that mapping backward? Now, I call this the inverse design problem. The forward design problem would be going from design space to Hamiltonian space, which is really, really hard. And we'll talk about it a lot through this workshop. But it is a well-defined and one-to-one problem. If you have a design, it implements some kind of behavior. And that is solvable, and you know it's solvable because at the very least the universe figures out how to solve it. The inverse design problem is not one-to-one, it is not well-defined, it is extraordinarily under-constrained. And I'll show you some examples of that. But okay, here's what you do. You probably start with an effective Hamiltonian and you say, okay, well, really, I want this circuit graph. And if you're like most experimental groups, you really only have a couple that you would work with, and you just sort of build up from there, because you really got to know what you're dealing with. So you have to have a lot of experience. And so you say, great, I've got a layout for that. Or you say, shoot, I need an inductor that has a gigantic impedance. Okay, now I need to go invent Josephson arrays. Or now I need to go invent space-lift junctions or something like this. Cool, PhD thesis, done. You make your layout. And you say, okay, I think this is right, but before I go to the expense and trouble of fabricating it, let me check. So you put it into some electromagnetic solver, something like ANSYS HFSS, or as we are discovering, it is much better to not pay for things. So you put it in Palace if you're in this workshop. And it has all these various hyperparameters, all these various knobs that say you can either be accurate or you can be fast. And you turn them as far towards accurate as you can tolerate, given the constraints of time and RAM. And this is hard, and this takes time, this takes effort, this takes compute cycles, which can be expensive. So you don't want to do this more than you need to. But you simulate it, and it says, okay, that means you're getting this circuit graph, or if you do some interpretations, even this effective Hamiltonian is coming out of this device. And you say, okay, that wasn't the one I wanted. It's off by these amounts. And if you know what you're doing, you say, well, okay, what I need to do is I need to tweak this, I need to make this capacitor smaller and make this junction bigger. And you do it again until you finally hit the target. And then one last time, you just turn all the accuracy up as high as you can go. And just make sure that you really did hit it, right? And then you hit a new flowchart where you adjust things to make sure that you can actually fabricate it and have it be roughly the correct design when it comes out of the fabrication process. You know, what you draw and what comes out of the fab are not identical. There are biases that are built into it, and you have to make sure you account for them. You send it over to your fabrication team. In my case, that's Daria. And he goes and works in the clean room for a couple of weeks and then comes back out. You do some room temperature testing to make sure everything you can test is okay. And you cool it down and you do completed characterization. In my case, that's often also Daria, but sometimes some other people. And you find out that it wasn't actually correct. Almost always you find out it wasn't actually correct. The simulations, the reality do not match perfectly. And you either decide whenever it's good enough Or you go back and you do it again. And the number of dollar signs here is roughly commensurate to the number of dollars that it takes to do this. So this is something that needs to be sped up. And this is something that needs to be simplified. And while they don't talk about it a ton, I'm quite sure that some of our sponsors here have been putting a lot of effort into trying to get this to be faster and cheaper. All right, let's define terms. I talked about effective Hamiltonians. Let me say what that actually is. It's something that looks like this. You have a collection of modes that are identified as individual modes. You say, here is a qubit, here is another qubit, here is a harmonic oscillator, here's an 8-level QDIT, it doesn't matter. But you're identifying them as separate objects. And then you're saying, okay, and now they interact. And generally, we're going to stick to the regime where those interactions are weak, where they are small compared to the self-energies. Sometimes you could have very strong interactions, but often it's actually useful to redefine the mode in that case. And likewise, if you have drives, you write them in terms of mode operators. So for qubits, these would be, X, Y, and Z. For general QDITs, these would be either diagonal operators or off-diagonal, raising and lowering operators. And this is a great level to work at when you're doing things like designing a gate, or trying to interpret spectroscopy results, or just like trying to figure out how your device is behaving once you already have one. But it's not a terrific way to go to look at an actual physical device and think what it's going to do, because it's not necessarily obvious what the modes are. And it's certainly not obvious when you go and put in a drive what kind of mode operator it uses. It's going to be X or Z, for instance. Or even if that's obvious, it's definitely not obvious what the strength is. What's that prefactor? So you go look at your device layout, and I want you to just glance around these devices. This is just a random collection that I pulled from the internet and from some stuff in my lab. These are all transmons. Every single device on here is just transmon devices. And as you can see, they look pretty dang different. At least 4 of them, as far as I can tell, are trying to do identical things and are really just drastically different. So there's a lot of choices here. You can't just glance at it and say, oh, it's doing this. You need an intermediate step. And so you go through this circuit graph. Now, okay, I want to first make sure we're on the same terms about what circuit elements are. So we're going to deal with 4 circuit elements: the inductor, the capacitor, the Josephson junction, and the quantum phase-slip junction. And the quantum phase-slip junction makes everything hard and annoying, and so we're going to ignore it almost all the time, because they're very rare. They're actually really hard to make. But the inductor is something that converts charge and current, flux and current, current being the time derivative of charge. The capacitor converts charge and voltage, voltage being the time derivative of flux. There's duality between them, they are conjugate to each other. The Josephson junction and the phase-slip junction are essentially non-linear inductors and non-linear capacitors. They non-linearly convert flux and current, or charge and voltage. There are resistors, there are memristors. Like, we're not going to worry about them. If you've got a resistor in your device, you probably did something wrong. If you got a memristor in your device, you definitely did something wrong, but you should probably go talk to like Intel, because they're going to be very interested in it. So you build these up and you make some arbitrary circuit. This isn't anything. We just threw together a bunch of circuit elements. You get something like this. What I want to point out here is that you have nodes. You have these dots here where we identify that place has a voltage. And everything that's just a black line connected to that is all the same voltage. And until you cross to the other side of a circuit element, you're going to stay at that one voltage. Likewise, you can have fluxes threading any loop. So that's this loop here. This phi2 is threading this big loop here. You can also have voltage biases, which I haven't drawn here. There's transmission lines, distributed elements. There's superinductors, which I haven't talked about. We're going to try to reduce everything to effective lumped models. Always write everything as a lumped element, as something that behaves like it has zero size. And just as voltage on one side and voltage on the other. This is, of course, an approximation because everything has finite size, everything's distributed. You may have noticed this, this node up at the top left here, and this node at the bottom right, we're not directly connected. That's an approximation. There's definitely capacitance between those two places. But it's an approximation we're going to have to make. We're going to say, okay, below this level, we're going to neglect capacitances or inductances between different nodes. And this right here, this level is generally the level at which you're going to think about designing your device. Not always, but usually this is what you have to do if you're trying to come up with a good qubit or a good system of qubits. Now, Lucas and David Paul are going to give a talk and workshop later in the session, I believe, for both beginner and advanced tracks on some nice techniques for doing this. All right, so once you have a circuit graph, you can make a circuit Hamiltonian. And again, you're doing things in terms of these nodes, these places in the circuit where you can define a voltage. And so you'll have a flux defined at one node, a flux at a neighboring node, an inductance between those two nodes, maybe some contribution from an external flux bias. And this whole term right here tells you, okay, that's the contribution of the inductive energy of the inductance between those two nodes. Likewise, you can have capacitance between those two nodes and a charge difference across them, maybe with some gate charge from a voltage bias, and say, okay, that's the capacitive energy contribution to that branch between nodes. You can have a junction between them, again, depending on the phase difference, on this flux, node flux difference is what I call it. Then you can add in your drives and everything. And as I apologize to Jens here, this is incomplete, but this is usually as far as you need to go. And it's really, really hard. There are many techniques for doing this. The most common is to try to generate a classical circuit Lagrangian, then turn that into a classical Hamiltonian, and then turn it into a quantum Hamiltonian by putting hats on all the variables. Which is literally the only thing you do to make it a quantum Hamiltonian. That doesn't work for everything. And so you need different techniques depending on what you're doing. In particular, quantum phase-like junctions really make your life hard. Non-reciprocal elements really make your life hard. Michelle Debray, I believe, is going to give some talk later about this and go into detail on some techniques for this. Once you have that circuit Hamiltonian, okay, now you can try to change it into an effective Hamiltonian. And so you have to quantize the circuit somehow. And you have to pick out that there are going to be modes which have mode operators, things like raising and lowering operators. You have to define whatever drives you've got in terms of those mode operators. And this can be tricky because sometimes the drive actually changes what the mode is. And so if you're doing that, you have to, go into some flow K theory. And you got to try to diagonalize it, transform it to some nice form, and make yourself a nice effective Hamiltonian like the one I showed earlier. Now, this is really hard. Jens is going to give a talk later about this and has done a lot of work on making software for this. Suffice it to say, even this is an extremely difficult, not only theoretical problem, but computational problem. This can be incredibly computationally intensive. And we haven't actually gotten to a physical device yet. We're just drawing lines on a piece of paper. Now, if you want to actually get to that circuit graph from your physical layout, you need to do an EM simulation. And wow, that is completely invisible. Okay, just pay attention to the left. This is just a little mock-up of a single transmon coupled to a meandering coplanar waveguide resonator coupled to a measurement feed line. Okay, you can simulate this. You basically solve Maxwell's equations on this arbitrary structure and find out, all right, well, what's the resonant frequencies of these things? What are the capacitances between them? What are the inductances? Can I turn this into an effective lumped circuit graph? I would say this is the most computationally intensive step because nominally this is actually a continuous space and you have to discretize it. And the finer you discretize it, the better your answer. It's very easy to get this wrong, and in fact, you can get this spectacularly wrong without realizing it. And we definitely need ways to do this better that don't just involve getting bigger computers with more RAM. I am sure that our illustrious sponsors at Google have access to some truly incredible compute resources. I don't think they have enough to simulate a 1 billion qubit CPU. I don't think that's possible. I think it's not actually doable, even if you turned a significant fraction of the Earth into a computer. So we need a better one. So Murat and Shanto and Ben will all give discussion on how to do this, how to do simulations, maybe how to do simulations a little bit faster, how to deal with things like flip chip. All right, so we've got these. This is sort of the approximate level. We have to deal with the fact that we don't just have isolated qubits or isolated resonators. We have to couple them together so that they can talk to each other. So we run 2 qubit interactions that we can do readout. So this is just a photo I grabbed of 2 transmons with a tunable transmon coupler in between them. Drive line, drive line, drive line, drive line, drive line. And then these 2 things are capacitors leading to 2 readout resonators. All right, this is a pretty dang simple system. All right, this is 2 transmons with 1 coupler and 2 readout resonators. And it already looks quite complicated. As soon as you put things together, you start to blow up the complexity of your system exponentially in the number of things you put together. And in fact, often what you're trying to do is make some effective Hamiltonian that you can't actually do natively. Like I want, for instance, a sigma z interaction between 2 qubits. Well, I don't get that with transmons. That's not a thing I can have. I can get XX plus YY, or just YY. And so I have to figure out how to get the ZZ out of that. Now, Andreas Wallraff and Daniel Sankin over in online will all give talks about how to do this in different contexts. We're trying to get these things to talk to each other. And unfortunately, that means they can talk to other stuff too. They can crosstalk. You can have pieces of your device communicating with other pieces of your device in a way that you did not want. Now, the one that sort of like comes up the most as like completely the designer's fault is what I'll call classical crosstalk or microwave crosstalk, which is simply that I'm driving 1 qubit and some other qubit somewhere else sees that drive field and responds to it. That actually could be very, very physically distant if you have some resonant coupling between them because they're like some fraction of a wavelength apart and you haven't done a good job of breaking up that mode. You can have qubits on opposite sides of the chip talking to each other quite strongly. So people do things like put these air bridge crossovers over their pieces of the device to kind of shield the field. There's been a lot of work, especially from MIT and now from several companies on trying to do 3 integration of these things. So Ben Jarvis-Frayne is going to talk a little bit about how to do flip chip and how to deal with crosstalk in this context. Still probably the designer's fault, but you get to blame your favorite theorist a little bit, is the fact that you also have quantum crosstalk, which is these 2 things are meant to couple to each other, but they're meant to couple to each other with a certain combination of operators, and some other combination of operators is also contributing. So if anyone here has heard of ZZ crosstalk or ZZ interactions as an error that shows up in transmons, you're trying to get something like an XX or an XZ coupling between 2 transmons, but you get a little bit of a ZZ coupling. You get a little bit of a transmon frequency shift, just depending on the other transmon state. And that can be a parasitic term that can mess up your gates. So for instance, in this device, the designers tried to solve it by having both a tunable coupler between their 2 transmons and also a resonator, resonator acting as a bus and sort of canceling out the ZZ with this multi-path coupling. The thing I really want to emphasize here is that crosstalk is entirely a solvable problem. All you need to do is make every single mode on the chip completely isolated from every other mode. Boom, crosstalk done. This will make your favorite quantum error correction theorist very upset Because the more coupling you have, the easier it is to run quantum error correction codes. There's all this exciting work now in these low density codes, which can work really well, can have very low overhead, as long as you can get every qubit to talk to like 15 other qubits. And okay, that's our problem. We got to deal with that. I haven't talked at all about the fact these are superconductors. The only place we've invoked superconductivity at all is just having Josephson junctions. And in fact, through almost the entire design process, people pretty much just treat superconductors like they're perfect conductors. Like they're just carrying current with no resistance, but that's not all superconductors do. They have kinetic inductance. There's inductance just related to the fact that Cooper pairs don't bounce around a lot when they move, so they have momentum. And if you try to accelerate them back the other way, they're going to have some inertia. You can get flux focusing. You know, superconductors don't like magnetic field to penetrate through them. They'll push it away. That can affect your couplings. But there's a finite penetration depth for that. That can affect things also. There's quantization of flux. If you've got a loop, you can only have integer flux quanta threading that loop. You can have these quantum phase slips, even if you didn't intend to make a quantum phase slip junction. So these are all things that you need to consider at some level. Now, Ofer Naumann and Hakan Trechi will both talk about this in different contexts. Now, I mentioned efficient design and efficient simulation. Again, what we're trying to do is take our design and figure out where in Hamiltonian space it lands. And okay, really, we're trying to go the other way, but let's solve the easier problem first. Let's solve the one that's actually well-defined. This black box here is this, you know, incredibly painstaking and complicated process of simulating and making effective Hamiltonians and figuring out what's going on. In the end, that's some kind of map. And that's a map that has rules. That's a map that should be well-defined, but it's an unknown map. Can anyone think of a field of science that is really good at finding unknown maps between one set of variables and another? ML, machine learning, AI in general. This is a perfect situation to start using AI. Mostly probably just sort of traditional machine learning, but there may actually be some role for things like large language models in this. You can think of design elements as tokens. So Shanto is going to talk about this some. You know, this is, I think, an area that is going to see a lot of active research in the next couple of years. Okay. That's all the material I wanted to cover. I need to cover some basic logistics. If that was like, yeah, okay, I've heard most of this, like that sounds fine, cool. Head over to the other room, go to the advanced session. If you were like, what the hell? You should probably stick it here for a little while. You can always go over there later. It's going to be easier to start in beginner and go to advanced than the other way around. The advanced session has a lot of different topics that we'll just jump between, assuming a common baseline of knowledge. The beginner session will step you through things, assuming that you've seen the previous talk. So if you're at all unsure, just stick in the beginner session. There's a bunch of software that you'll need in order to participate in the workshops. You'll need Qiskit Metal. You will need Squads. You will need SQD Metal. You will need Palace. Is there anything else? No. Okay. There's one more thing for NVIDIA where you have to sign up where we send instructions on it. Please make sure those are already installed. All the latest updates. If you haven't gotten this done or if you run into problems, talk to us during lunch. And by us, I mean Shanto. All breaks, all lunch and everything is going to be in the other room. We're not allowed to have food and drinks in here. Sorry. Finally, late Tuesday and Wednesday, in the advanced session, we're going to have breakout sessions. And these are going to just be small groups where we'll just like find a room somewhere or just find a corner of this room or something and talk about some particular advanced topic. So one that's already been planned is that there's all these open source software packages, which are really fantastic and need to be maintained. And currently they're being maintained in people's spare time out of the goodness of their hearts. I'm sure you all have tons of spare time. We're going to try to formalize this and maybe even compensate people. So we want to get some maintainers groups going. So if you're interested in this, please do join that. We need to do educational resource creation. I'm definitely going to host a breakout session for that because I've been trying to teach this stuff for a while and God, I need a textbook. I'm going to be ambitious and say we're going to do this again next year. So if you want to be involved in that. And also come drink quantum beer with us this afternoon. I promise it's just as good as classical beer. Last but not least, there is a Discord channel for the workshop. So if you run into problems with anything, or just want to like chat with people, you want to heckle the presenter or whatever, use this. And with that, I think I've wrapped up the kickoff. I do want to make sure that everyone is okay with everything. Are there any questions on any logistics, anything? Oh, yes. So on Thursday, so Monday, Tuesday, Wednesday are going to be fairly similar. You know, we're going to have talks, some workshops, beginner and advanced sessions running in parallel. On Thursday, the morning is going to be a long sort of workshop session with NVIDIA, and that is going to be joint. Well, I think they're going to have people in both rooms. So, you know, just find a place to sit and you'll run together. And then in the afternoon, there's going to be a panel discussion, which Zlatko Minov is going to moderate with me and Dean Koch and Michelle Devray and Andrew Bestwick and Andreas Wawa. And we're just going to talk about design and what we think needs to be done and, you know, where we see this going. And hopefully that should be interesting. So please do come join if you're interested. Finally, if you have any questions on logistics or on anything like that, please don't ask me. I have no idea. This is not my campus. It's one of these guys, and they will point you the right way. All right. So with that, please find your room. We'll start this off.
I don't even have a mouse. Wonderful. I'll go over.
People online, can you hear my voice okay?
Great.
All right, we're good. We're good.
You got the camera working?
Camera's working, just don't run into this board.
Why not?
Let me see if I can find a way. Oh, you know what we can do? We can use the fact this is actually a tripod.
Suppose I shouldn't stand here, right? I'll block it.
Yeah, I think if you go over the other side. I mean, it only needs to see you. It only needs to see you, the screen share, so.
So I like to point at the screen.
Yeah, so let me get you. I got you.
That is